So let's think about the intravenous fluids that we might use. Well, the first thing I think we should say is that if we're giving large amounts of fluid, it needs to be warmed, probably up to about 39 degrees centigrade, preferably in a water bath. In an emergency situation, if you need to, you can actually warm it in a microwave if it's just crystalloid fluid. And make sure you shake it up, otherwise you get hot bits and cold bits. But ideally, just warm it in a water bath, set to 39 degrees centigrade, and then by the time it gets to the patient, it's probably gone down to about 38 degrees centigrade anyway. And this is important because if we put a lot of cold fluids into a patient, we're going to cool that blood down and indeed cool down the whole patient. We can actually contribute to hypothermia. Because if the blood is cold, the platelets are not going to aggregate properly. The coagulation cascade will not work properly because it's all based on enzymic activities, and enzymes work best at 37 degrees centigrade. So warmed. In the first instance, after hemorrhage, we're probably going to be given crystalloid solutions such as normal saline, Hartmann's, which is a Ringer's lactate type solution. So crystalloid fluids probably in the first instance. Colloids can be given after consideration, but normally crystalloid fluids in the first instance for resuscitation after significant hemorrhage. And if there's been a significant bleed, an adult might require 1 to 2 litres of fluid given fairly quickly to try and restore the intravascular volume. But of course, this is based all the time on individual patient assessments and on titration of the patient's response. There can be no blanket rules. But in most cases, be prepared to give 1 or 2 litres fairly quickly. Now, in a child, the initial fluid resuscitation is going to be something like, well, it's going to be, the guidelines say, 20 mils per kilogram. So weigh the child or estimate the weight of the child. An initial fluid resuscitation probably going to be 20 mils of crystalloid fluid per kilogram of the child's body weight. Now, if more than 1.5 litres of blood are lost in an average-sized adult, we're probably going to need a blood transfusion as well as the crystalloid fluid. So at more than 1.5 litres, we need to be starting to think about blood as well. And ideally, we want to give cross-matched blood. Now, everyone knows that there's blood groups like A, B, O, AB, rhesus negative, rhesus positive. Everyone knows about that. But the clever people in the haematology labs know about another 8 or 9 blood groups that I've never heard of. There are extra blood groups, and they can cross-match them all so that the blood you get is precisely the right blood for that patient. That's fully cross-matched blood. But of course, in most labs, that's going to take about an hour, and by that time, the patient might have bled to death. So if we can't get fully cross-matched blood, the next best thing is type-specific blood. So that means if the patient's A positive, they get A positive blood. If they're B negative, they get B negative blood. If they're O positive, they get O positive blood. It's just the same type. And it's overwhelmingly likely that that will be okay. If you get the ABO recess bit right, I guess you're kind of 95% the way there to being a safe transfusion. So cross-matched ideally, type-specific is the next best thing. But if there's not even time for that, in a case where the patient is bleeding to death, if there is exsanguinating hemorrhage and it's an absolute emergency situation, then we can give them type O packed cells, probably O negative packed cells if they're available. And that's described as the universal donor. So in an emergency situation, type O negative blood is acceptable. Also, think about the possibility of auto-transfusion. You might have seen these on surgical units where blood's taken from a wound drain and then processed in some way and put back into the patient. Or a hemothorax is another good example where the blood can be collected. So when the chest drain goes in, the blood can be collected. Normally you'd add something like sodium citrate to it as an anticoagulant to stop it clotting before it goes back in, and then run it back into the patient if you've got the correct facility to do that. And of course that's the patient's own blood. You're taking it from a third space where it's completely useless and putting it back into the intravascular compartment where it is intensely useful.